Good morning. You're probably wondering what this talk is about. I just stuck this down. I'm going to sort of touch on these things: performance, correctness, blame, and guilt. And first of all, performance. There's a common thing of people who design programming languages care about correctness, not about performance. The performance problem is solved. It's really easy. If you've got a program, you take a program and you want it to go 1,000 times faster, just wait 10 years. It goes 1,000 times faster. So that's solved. If you want it 1,000,000 times faster, you wait 20 years. So that problem's solved. And that's why Erlang's really fast today, because we waited a long time. So I used to tell the management at Ericsson, so all we've got to do is write the software in a beautiful way so that it's correct. It doesn't matter if it's slow, and then we wait, and then it'll be fast enough. And then we can phase that in and throw out all this rubbish software. It'll be fine. So performance is solved. Correctness. Well, if you read Kernighan and Prager Kernighan and Ritchie and things like that, they will say, make it right before you make it fast, because they know to make it fast you wait 10 years. But they know that the most difficult thing to do is to make it correct. Now, why do the designers of programming languages want correctness? Well, it's because if you write a program in Erlang and it turns out to be incorrect, I get the blame. But if it works, you get the credit, you see. So programming languages designers really don't like their children to be abused, and they don't like errors to occur, and because they get blamed. And of course, if I actually go around and say, well, would it be a good idea to design a nuclear power plant control system in Erlang? And I say, yeah, well, it'd be better. But by that I mean, yes, it'd be better than doing it in C++ or Java, because I think that's the best bet. But if you guys went and did that, and if the control system failed and killed a few million people, I would feel very guilty about that. So that's why I'm interested in correctness. Because I don't want you to go and kill a lot of people, and I don't want to get blamed. So to get to correctness, I have to tell a few stories, and I'm going to talk about some design patterns that are in Erlang. These are what Christopher Alexander calls the things without names. They are so obvious that we don't give them names. I'm going to give some of them names. And I'm going to highlight two design patterns which I believe to be central to Erlang. And I'll try to tell you why. So it's a rather checkered story. Erlang will sort of come in at the end, perhaps not at the beginning. You might not see where I'm going in the beginning, but the threads will draw together as we go on. So, right, so are you sitting comfortably? Yes, good. Right, then we'll begin. So, once upon a time, in a far-off, snowy land, Gunnar M. Eriksson asked me a question. He was the managing director of LMTEL, where we worked at the time, and he said, he sat down next to me at lunch. He said, look, I've heard Erlang's pretty good. You know, people tell me Erlang's... He's not a technical guy, but he talks to people. He says, Erlang's pretty good, and C++ is pretty good. So we've got this Erlang, and we've got this C++. So why don't you just sort of glue them together? And so I replied, well, Erlang's like Meccano. Meccano's very good. Did any of you have Meccano when you were kids? Yeah, I loved Meccano. So I built all these things. That's not me, actually. So Erlang's like Meccano. You can build wonderful things with Meccano, and they're absolutely beautiful. And C++, it's like Lego. You know, Lego's wonderful. I didn't actually like Lego as much as Meccano, but it was okay. My kids like Lego more than Meccano. But there isn't any glue. The glue that you use to glue Meccano and Lego together doesn't work. Can you imagine making something out of Meccano, all these little metal things, and something out of Lego, and you just what do? You go to the store, buy a big tube of araldite, stick it together, and it's a mess. Right. So, what's all this got to do with Erlang? Absolutely nothing, you're thinking, but somehow. Okay, so I want to look to the basics of programming. So at the deepest fundamental level of programming, we have black boxes. So that's a black box. Well, sort of black circle, or a process. And really, we would like two levels of abstraction. One level of abstraction says what's going on inside the black box. And the other level of abstraction says what's happening between black boxes. So this is a C or a C++ or a Java or a blah or a blah or a blah or a Ruby or a program, because they're sequential. You've got one black box because it's a sequential language. Well, Erlang's slightly different. That's Erlang. You've got lots and lots and lots of little black boxes. Well, round things. And they send messages to each other. And you can derive an awful lot of information. So this has been changing with time. So I saw the Concurrix displays yesterday, and they were showing exactly these pictures and visualizing them in a beautiful way. And it struck me that this is fantastic. This is a quantum leap in abstraction, because it says we can understand how a system works without understanding what's happening inside the black boxes. Now, most people have been looking inside the black boxes and trying to understand how they work, and I think they've been looking in the wrong place. They shouldn't be looking at inside the black boxes to understand how programs work. They should be looking at how the things are interconnected and what they do. Right. So if we've got something like this at a macroscopic level, what does it look like at a microscopic level? Well, we have to understand this. Now, why do we want to understand this? What's the reason for wanting to understand that? Well, the reason is that programs don't work. Okay, they haven't worked for years. They didn't work when I started programming. They still don't work now. And I think the reason for that is that we can write little programs, but when we write big programs and glue them together, they don't work. So that's a glue problem. So let's look at the glue problem. And am I the only person in the world who thinks that? No. Oh, good. But I thought I'd find some quotes. So, Richard O'Keefe, he writes on the mailing list wonderful, insightful comments. And on his homepage, he said, I would sum up my research interest by saying, everything connects. And my biggest problem is just about everything is interesting. And what have we got? My biggest concern is that most programs don't work, and hence my interest in software. So I think, Richard wrote this, but this could be on my homepage. I could write this. This is exactly what I think. Yeah, everything is interesting. Everything does connect. Yeah, programs don't work. So, is there anything we can do about this? I'm going to have a quiz. Actually, it's a quote. The quiz is to name where the quote comes from. And there's one person in the audience who I think will get it really quickly, because they said yesterday. So they're not to answer. I don't want you to answer. We'll leave you guessing until the end. Okay. So here's a nice long quote. I'll read it to you. It soon became clear from a study of the system. It soon became clear that a study of the system was nearly impossible. Its dimensions were simply awesome, and documentation accordingly sparse. Answers to questions that were momentarily pressing could best be obtained by interviewing the systems designer, who were all in-house. In doing so, we made the shocking discovery that often we could not understand their language. Explanations were fraught with jargon and references to other parts of the system which remained equally enigmatic to us. And you're thinking, hey, they're describing my company. This is Ericsson. Fantastic. No, it's not. It's not Ericsson. But it's pretty typical. There's another quote from the book, same book. And had I not repeatedly experienced an inadequate and frustrating program, could be programmed from scratch in a fraction of the source code used in the original design. Yeah, sure. Why do we write things from scratch all the time and re-implement things? Because it's quicker than finding another program that does it. We can't find that program. And if we did find it, it does something slightly different to what we wanted, and it's quicker to write a new program than modify the old program. Okay? So we all know that. And a clue to where that, if you can identify the guy without the underpants on, you'll know where the quotes come from. So take a look at the guy without the underpants, and then you'll guess where it comes from. Right. So Joe's law. Frameworks grow in complexity until nobody can use them, right? We're laughing for it, it's true. And that, well, like Bill Clinton, that's because the bits don't fit together, stupid, right? So let's look at some things, okay? So inside black boxes, you find programs, and programs communicate. I don't really care how they work. Two systems are equivalent if you can't tell the difference by observing their inputs and outputs. It's a principle of observational equivalence. It doesn't really matter if they're functional or imperative or monads or any of that rubbish. It doesn't matter, provided they're equivalent. Now, a lot of people spend an awful lot of time looking inside those black boxes and asking the question, what language should we program the black boxes in? And then they get all excited and they say, let's use Ruby or Rython or Drython or Blidlon, Fortran, Godblong, Tang 2 or whatever it's called. But they're looking in the wrong place. What's inside the red arrow? Why aren't they looking inside the arrows to see what's going on there? Because that's telling you how the things interact. I don't know how your brains work inside. So if we want to talk, we have to use a common language, like English or something that all of us understand. Understanding English is much more important than understanding what's going on inside our brains, because I'll never get inside Creston's brain to figure out how his brain works, and he'll never get inside my brain. And we just send these messages to each other. So sometimes when programs communicate by sending messages, it works quite nicely. When it works quite nicely is the messages are like files. So a file's a message. So if we make a JPEG file or PDF file, we don't care how it was created. And we've got this good notion. And that's because it's a sort of one-off exchange and what's in that thing is well specified. But when we start sending messages backwards and forth, we get into a bit of a mess. So to understand this, I want to look at the history of connecting things together. Right, so this is a quote from McIlroy. McIlroy was Dennis Ritchie and Brian Kernighan's boss at Bell Labs. And this was the kind of specification of Unix. And there's some typewritten notes. If you go to Dennis Ritchie's, there's a web page, still his website's still there. In fact, passed on, and it's got these wonderful source of information. And there, this is a spec for Unix, okay? And it says, point one, we should have some way of coupling programs. What does he say? We should have some way of coupling programs like a garden hose. Screw the segments in when it becomes necessary to massage the data in some way. So this was the pipe, the hose pipe. My shadow's coming up. He conceived the Unix pipe which allowed programs to work together with no knowledge of each other. This is a fantastic invention, okay? And these are quotes from this webpage. Points one, garden hose analogy connection is the one that ultimately whacked us on the head to best effect. Boomf! And you understand it. Yeah, that's a great idea. Doug he forced it on them. I don't think they wanted to do it to start. That's what Kernighan and Ritchie say. Right. So pipes. Pipes are wonderful. They are beautiful things. Yesterday, in the keynote there, we said that, another thing about pipes is you don't care what's going through the pipes. It all works nicely. You don't care if it's water or oil or something. It's how they're connected together that's the interesting thing. So this is plumbing, okay? So actually, as I was preparing this lecture, it sort of was a bit funny because I thought, I'll talk about pipes. And so I wanted an illustration of pipes. And I searched for this, and I found this thing, and it was on a website called Plumbing Disasters. And so I thought, hang on, let's read these things. And I thought, they're describing software. It's absolutely fantastic. So when you move into a new house or property, try to locate the main stopcock which shuts off the water supply to the house. Do not wait until you have a major problem until it will be too late. So when you move into a new data center, try and find where the major switch is and the Ethernet cable comes in through the wall. Make sure you can turn it off if there's a problem. Right. Fit service valves on all your water pipes. and things. So you can turn them off, yes? So when you've got your server, make sure you can turn them off and move the cables around. And yeah, wait a moment. If you've got a leak and you've no idea when it's coming from, call a professional plumber who will analyse your system, you see. Now, you guys have built these tools to find out where the leaks are. You're the professional plumbers. And oh, look, it's leaking over there. And water all over the floor. And there's all sorts of things about plumbing, like if you've got a big tank and you pour water into it and water goes out of it, if the water goes out of it slower than the water goes into it, then it'll overflow, right? That's a web server, right? More requests than you can satisfy, it overflows and it doesn't work. So if you go to sites on plumbing, search for plumbing disasters, and you'll find a whole list, and they're a software architecture for you, right? And so when it becomes it's even worse when the wires are easy to connect. So this is a typical server hall. Have you been in this? Do not touch any of the wires. When I had a company, we used to go, Bluetail, we used to go into these servers, like, don't touch anything! Sometimes they said, we would sort of pull the cable out, take like a week to figure out why the network didn't work and where you should plug it in again. I mean, it's good fun, that stuff. So, there's an answer to that. Clean your room. Your mother told you when you were little, and it's quite easy. And once you've cleaned your room, you've got a nice, tidy plumbing. This is a nice airline system, okay. So it's got pipes and it's got boilers. And we can do boiler change on the fly. This is how I used to explain code change on the fly to airline people. So if you want to change your boiler, you make sure it's got, pointer here, yeah, you make sure it's got valves there, you turn them off. Turn them off, turn them off, turn them off, and then you get a hacksaw and you cut them off. You lift out the boiler, you put a new boiler in, weld them on, and you turn. That's boiler change on the fly, and that's how we do it in Erlang. So it's all quite good. And so because we can take our inspiration from this, I'm thinking maybe we should inspire the boiler industry. So I think we should invent BoilerNet. You could do boiler change on the fly, boiler balancing, 6 nines boiler reliability. Boiler services on demand, water on demand, poops down the pipe, all sorts of things, because we don't care what's in the pipes. So it's all quite fun. Right, so client-server interactions. How do they interact? A few weeks ago, I discovered a program called Chandler. And I was very taken by it. This is a screenshot of the web version of Chandler. And that's not my clone. I'm writing a clone of it, which you can download from my website, my GitHub page. Sort of almost at that level now, not quite. Chandler's a brilliant thing. It's a brilliant program. Does anybody know it? Yeah, isn't it brilliant? It's lovely. It's to-do lists, but with a twist, because to-do lists are stupid, right? They say to-do, tick, yes or no. But hang on, to-do isn't binary, and it's things that are done are not done. There may be. So Chandler uses a triage model from the hospitals. It classifies tasks into urgent, do them later, and done. And it realizes that tasks can be reclassified all the time. So Chandler said, well, you start off with this task. I'm going to do it now, so it's urgent. And then you sort them by that, and then you say, I'll do it later, so you reclassify it as later. And you sort of manage it that way. And it also says that the value of to-do is not a Boolean, which is yes or no. It's grey, it's text, and it changes with time. And so it's very nice. I love Chandler. So I was writing this, and I thought, oh, they've given up on this project, which is a shame. And I thought I'd like to re-implement it. And I thought to myself that this should be easy because they've written the client and a server, and all I want to do is write the server in Erlang. I'll keep the client. And so I thought to myself, well, hang on, this should be something that's easy. We've got a client, and we've got a server, and they're separated by a socket. So that's easy. I'm just replacing one of these. All I have to do is reproduce what I see on the wire. It should be easy. But it's not. Because the client is described by a state machine, and they describe it very nicely. You know, when you do client, you describe the state machine of the client. And the server is defined by a state machine. That's all done very nicely. But who describes what's seen on the wire? Well, nobody, because it's not in the description of the client and it's not in the description of the server. It's in this, remember the diagram of the red line? It's in the middle of the red line, but nobody's described what it is, so we don't actually know what they do. And they didn't think it was important to describe this. So if you read the client code, what's on the wire is sort of there, dotted around in a weird kind of way. You can't find it. If you read what's in the server, it's sort of dotted around in a way. It's not thought to be important, so it's not described. And then I thought, well, okay, let's do the client. Okay, I'm not very good at web programming, so I looked on the net and I found this quote. I thought it was nice. You know, when you're choosing how to build the client, oh dear, you know, I can't keep up with all this Ruby on Grails and nails and stuff, oh dear, right. So, let's see. Is this related to the first problem? So we've got a problem. The bits are connected together, but we don't know how they're connected together because we haven't described the connection. And then there's another problem. Software doesn't work. We don't really know why. Right. So what would Gandalf say? Well, let's see. Suppose the bits were connected together and we did know why. And then if the software didn't work, we would know why. Right, so what do? We put a contract checker in the middle. This is the notion of a contract checker. That describes what's going on the wire. That's a sort of legal thing. And I learned this many years ago. This was my first big mistake in software. You know, I was about 28 or something like that, and a good age to make your first major disaster. So I worked for the Swedish Space Corporation, and we were building a satellite, and the satellite was delivered by Boeing, and Boeing had written a load of software, and I'd been involved in the contracts and everything, and we wrote a contract, and we wrote a test document, test procedure. 2 weeks of testing, heavy testing, I had to pass all these tests. It was to be connected to some other equipment that also had tests, and I wrote all that stuff. We went to Boeing and tested it. It took 2 weeks, and I signed off. It works. I went to this other company, and I signed off. It works. We took them both back to Stockholm and connected them together, and they didn't work. Right. And then I went to Boeing and said, when I connect it to the other stuff that it's supposed to be connected to, it doesn't work. And they said, well, that's your problem, mate, because you signed the agreement that it's accepted. And I went to the other people and they said, well, that's your problem, mate, because you signed the agreement. We had to rewrite all the bloody software, all of it, to make it work. I mean, so I never believed this stuff, because there wasn't a contract for what was in the middle. There was if that was Boeing at one end there, and that was our other supplier there. We had contracts with both of them. Fine, but when we connected it together, it didn't work because we didn't have a contract for what should happen in the middle, and we should have brought both of those things together, put them in the lab together, put the contract checker in the middle, and the contract checker would say which of those two guys is faulty. Otherwise, it works. That's the contract checker. Contracts, right. So, purpose of contracts, as you all know, is to assign blame when things go wrong. That's why we have lawyers. If nothing goes wrong, you don't look at the contract, but if things go wrong, you look at the contract and you assign blame. So here's the contract checker, sort of, it will pounce on you if you make a mistake. So I kind of thought, well, this is it's funny. So there are companies that make clients, and there are companies that make servers. So there's like 2,000 RFCs or something for major things. So there's like 2,000 business ideas. There's 2,000 companies waiting to be made there. To go and, that's not a business idea, that's a meta business idea. It's how to form 1,000 companies. Things like Wireshark would be greatly enhanced if they not just sort of printed out the binary messages that go backwards and forwards, if you had a contractual thing there that said that is now not following this contract. Right. So if we've got contracts, where do we put them? Well, it doesn't really matter. Might put them in the cloud, might put them somewhere else. How are we going to write the contracts? Right, so let's look at a bit of history again. Postel's law. An implementation should be conservative in its sending behavior and liberal in its receiving behavior. This is what I call his making matters worse law. Because, you know, if you get a sort of message that comes into your system and you're kind of forgiving and say, well, you really meant to do that, so I'll correct the error, and you pass it downstream, you're just making matters worse. It didn't matter when Postel was doing it. He only had sort of two things connected together, and you didn't have malicious hackers in the network. Now we have hundreds of things connected together. And if you pass errors on downstream, you just make matters worse. Also, Postel was assuming that the people who were sending him bad data were doing so for good reasons. You know, they just made a mistake in their code. People might send you bad data for bad reasons. So, for example, if I send an HTTP request, byte at a time with a 1 second delay between, and open up 5,000 sessions to do that, it's probably a denial of service attack. But Postel would say, oh, it's just the programmer who's made a mistake, I'll correct this. So it's not a good idea to do this. So we should actually do the opposite. This is Joe's law. Crash, 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 crash as soon as possible. Right. Oh, and fail early, fail fast, crash, no defensive program, don't accept data, blah, 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 blah. But it's the don't, these are sort of fail early, fail fast, crash, and all that stuff I usually say. They are all instances of this rule, which is the don't make matters worse rule. Okay, that's a meta rule. Right, we don't want to make matters worse. Right. Postel actually had a little bit of a point, because at the time you only had sequential programming languages. If you've got one process, crashing's a big deal. Nobody else can correct the error. Erlang is not a problem. You've got zillions of processes floating around, and they have different roles. Some do jobs, others correct errors. So if you're thinking in, you know, this one process, horrible, you know, C++, Java, Ruby, you name it. Horrible, because you've only got one place to fix the error. In Erlang, you've got zillions of alternatives to fix the error. What about the language on the wire? Right, so Postel again. I think, I was going back in the history of RFCs. The first RFC I could find that used this protocol of a verb, or keywords, mail from, and a numerical reply, 250 OK, seems to be an RFC 821, which was the simple mail transfer protocol by Postel and his friends. Bad ideas in computer science anywhere are sticky. You see, if the first idea was a bad idea, then because it worked, people sort of repeat it into the next idea, right? So, 1,791 RFCs later, we get HTTP. Get 200 OK. Right. No. No, I don't have to tell you why, do I? I mean, it's silly. Okay, so what do you want? We don't want thousands of ad hoc parsers. Okay, it's a big opportunity. 1,791 parsers have to be written by 1,791 companies, and 10,000 programmers have to write this stuff. But it's ad hoc. All those parsers are ad hoc. There's no type system. There's no formal definition. There's an English definition of the protocol, and it's very inefficient. So what do we want instead? Well, we can rule out XML. Well, we could have used Postel. No, we couldn't have used XML and JSON because they hadn't been invented. Possibly could have used Lisp. It would have been good. Here's some other alternatives. ASN1 is very nice. The Erlang external format is very nice. This is the wire format, and there's something called UBF, which I invented, which is beautiful. UBF is not widely used. Anybody use UBF? Oh, great. Isn't it lovely?
It's wonderful.
Thank you. Now, there's a problem with UBF, and that was my publicity model. Right, so I did UBF in a 3-week period. I wrote a paper about it when I was at 6. And I posted the code online there, the tarball, and then I wrote 1 or 2 posts to the Erlang mailing list, and then I didn't really get much interest. So I left it for 10 years, and about every 10 years I wake it up and say, I did this UBF stuff, anybody interested? Nobody's interested, you see. So this publicity model is wrong, okay? So you can go and look and tweet, please tweet, and if you've got an hour or half an hour, it'll take you half an hour to read it. Read it. Might be half an hour well spent. And all tweet about it, and all go there, and probably 6 will see a denial of service attack there and wonders what happened, so it will be very interesting. Right. So that's a universal protocol. I'm going to show you what you can do with universal protocols a bit later. And of course, universality, the nice thing about these 3 things, ASM1, Erlang external format, UBF, they're not parsed. They're reconstructed terms. All these, JSON, list-based expressions, XML, need parsing when they come in. And parsing means you've got to look at every single character. There's no alternative to that. These are reconstructed. Things like ASM1 will say, OK, now there's 500 bytes, woomph. So you don't need to look at those 500 bytes, you just hop over them. So you reconstruct the terms rather than parsing them. UBF is just it's not a data structure that you send. It's a program. It's a byte-coded program. It's a virtual machine that you execute when you get it. And it's got curly brackets in, but the curly brackets are opcodes in the virtual machine, because the byte code for a curly bracket can be used as an opcode in your virtual machine for a byte-coded machine. So it looks as if it's a term, but it's not. It's a program. And these 2 things, these are my favorite friends in Erlang, term to binary and binary to term, because they're parsers. Binary to term is a parser. Well, sorry, it's not a parser, it's a term reconstructor. It allows you, these together allow you to serialize and deserialize anything and put it in a database. That's why you can do, these are the basis for the sort of NoSQL databases that are written in Erlang. That's why they work. That's the fundamental thing why they work. Right. And once you've got universality in messaging, you can write universal programs. So this little program in Erlang, we all know Erlang. This is great. Most conferences you don't, you see. So this is an email server, an instant messaging thing, and an HTTP server or an FTP server, whatever you want to call it, right? It does all 3. Because what's email? Yeah, you receive email from you open an inbox and you write to it. Okay, that's what an email client does. Hasn't got a GUI. Okay, so it's not very pretty, but it's the logic. What's that? It's instant messaging. What is instant messaging? You get a message and you display it. That's what instant messaging is. There's nothing more complicated than that. Okay, it hasn't got a GUI, but it's still instant messaging. What's that? That's anything you like. It's FTP, it's HTTP. What's the difference between FTP and HTTP? Get a file from a remote machine. That's what it is. That's the guts of the thing. Okay, it's got keep alive and all this stuff on the socket, but that's sort of added extra. The fundamental utility of that program is to transfer files between machines. But hang on, I just do all 3 in one process. Why can't I send instant messages to a file? Why can't I email a room? I also, it's silly, you know, you can email people, but you can't email things. Why? Well, if I want to book a room, I just send an email to it. Email to room number 203, can I book you next Tuesday? Yeah, thanks. You know, I mean, why do we have these different things? It's crazy. Just have one universal thing. Right. So, how are we going to write the contracts? How are we doing for time? Ooh, yeah, oh, all right. Contracts. Well, can't use APIs. APIs don't work. Here's an API. This is what you see in Erlang. Open a file, close it. Open a file gives you a OK handle or error. Close it, give a handle, OK. Read it, gives you a handle. Do you think that's OK to describe a program? No. Of course it's not. Because that won't tell you that that program is illegal. It type checks in any known language in the world that has that kind of specification. It says, OK, open a file, close it, and then read it. Great, that's wrong. Doesn't work. The type system says it works. So it doesn't tell you anything. So the protocol has to do more than an API, more than a type signature. Right, so let's try and write one. You have to add a finite state machine to a type system, and that gives you a contract. So here's a finite state machine added to the API. When you're in the state start and you get open, okay, and you're in the state ready. And when you're in the state ready and you get close, you go to the state closed. And when you're in the state ready, you can read and it's okay. So if you had the type system like that, it would tell you that your program was incorrect. That's what you can stick in the contract checker between the two things. So let's write some simple contracts. Here's a website login protocol. The contracts are 4 tuples. You've got a state in and a message state, and you've got message out and a state out. And there we are. It's a finite. Oh, and then I learned a big word yesterday at the keynote. It's a mealy machine and a monad. So this is very good stuff. And so there's the mealy machine that tells you to do logins. I wrote it in JavaScript just for fun. Because I actually wanted to run it in the client, not in Erlang. So here's a JavaScript client, and here's the types. Oh, there's a state machine. Some people like that, other people like things like that. The two are equivalent. And here's the type system, and here's an example sequence. And we just run it through the contract checker, and it'll find errors. So it assigns blame when things are wrong. That's very nice. That's our contract checker. And that's one of the abstractions that's incredibly useful when we're gluing large systems together. And the idea is not much used. But I was at Facebook giving a talk, and I met their technical director chap. What was he? Who was it? I forget the name. But we talked about that, and I said, yeah, we should have contract. And he lit up like a candle, and glow. Yeah, I've been telling people for years, he said. So contract's good news. Assigns blame when things go wrong, formalizes the relationships between the endpoints, and it's written in a well-understood language. Right. Now, there's another abstraction. This is the abstraction without a name. But you see, we're all using it when we write Erlang, but we don't give it a name. It is so bloody obvious that we don't even know we're doing it. Right? Because when you write code like this, forget it, I'll go forward. The example I showed you. When you write code like this, you are communicating with things on the outside world that you believe to be Erlang. This thing I showed you, this bit of code that could do email, instant messaging, and file transfers, was listening for Erlang messages. So you believe that whatever it is out there is not FTP or something, it's Erlang. That's your belief. And there's an abstraction I call the middleman. I've gone wrong. It's the middleman. So the middleman's job is to sit between the outside world and create the illusion that the outside world is Erlang. Okay? So it doesn't matter. If you've got HTTP here, you have the middleman, and out come Erlang terms. Now, Erlang programmers don't really realize that because you're inside the Erlang world and everything is Erlang terms. So this is the thing you've forgotten, because all these drivers, they're in the libraries. So when you want to do something new in Erlang, you implement a new driver, stick it in the library, and then you start getting Erlang messages coming to you, right? So imagine, this is fantastic. This is a fantastic abstraction, because imagine you want a system, and it's going to speak Spanish, Japanese, French, and English, and you've got to join these things together, like, well, where's the thing like this? So this part of the application has got to understand English and French, and it's got to learn Spanish and Japanese, and so on. Oh, this one's got to understand English, Spanish, and Japanese. Okay? So writing that code is an order n squared problem, okay, where n is the number of different things. You've got to have, they interact in n squared, well, actually, n times n minus 1 over 2, but that's order n squared. Okay, so if you put the middleman in like this, it becomes a complexity order n, not n squared. So here's the middleman. Okay, English comes in here, Spanish comes in here, Japanese comes in here, and we convert to a common language that everybody understands, for example, Swedish. And then we write all of these in Swedish. Och det är jättelätt. Det är fantastiskt lätt, för alla förstår det där. Apart from the odd person who doesn't speak Swedish. So this is why, there's a secret plan in Stockholm. We're writing everything in Swedish and sending them all in Erlang, and all the messages running around. So the middleman is the bringer, oh, sorry, I was going to say this slide. The middleman is the bringer of order, okay? Because it makes you think that everything in the external world is an Erlang process. And this is the Erlang model. Actually, the Erlang model of the world has more than the middleman. It's got the failure model as well. So Robert and I keep going on about, oh, no, the Erlang model, you've got to make everything look like Erlang processes. And the reason for that is that it turns order n squared problems into order n problems. Right. So the middleman is the Higgs boson of Erlang because it imposes order. The Higgs boson is the creator of mass. All particles get their mass because of the Higgs boson. Yeah, you know that. I have a secret history. I used to be doing I'm a failed PhD in elementary particle physics, which you didn't know. So actually, when the Higgs boson came, I was actually explaining with Z0 mesons and Feynman diagrams on the blackboard how it worked. It's quite good. And I subscribed to particle physicist jokes. So, you know, there were Higgs boson walked into a church and the rector, the vicar priest said, "You can't come into this church. You're not allowed to go to mass." And the Higgs boson said, "Well, why not? I am the creator of all mass." And the particle physicists tell jokes like that. And there's a whole sort of subculture of particle physicist jokes, which... a round of applause, please. Yes. Thank you. Right, so the middleman brings conceptual integrity to the system. Because what appeared to be a mess, what appeared to be thousands of different protocols, now becomes one protocol. What appeared to be thousands of different languages becomes one language. What appeared to have an n squared complexity becomes an order n complexity. And I believe this is why things like ops code in Facebook, where they're dealing with large numbers of protocols, by converting them all into Erlang and working internally in Erlang, they've reduced this from an order n squared problem to an order n problem. And if they haven't thought about just sort of doing it that way, they should think about doing it that way, because that's the way to make systems. Right. Quick commercial break. Very quick commercial break. The second edition of my book will be out on April the 17th as a PDF file, and I'm actually taking up middlemen and things like that as specific ways of programming, just to try and popularize this idea a bit more. End of commercial break. Tweet, tweet, tweet. My editor said I should do that. Quiz, right. So, who's the man without the underpants? Oh. Any takers? Come on. No! Who's the dame with the funny nightie? No? That's Oberon, the king of the fairies. That's his Mrs. Oberon. And Project Oberon. And these quotes are all from, it's a fantastic book. Have you read it? Who's read the book? Yeah, isn't it great? I mean, Nicholas Wirth is an inspiration to everybody because he decides, I don't know how old he was, about 64 or something, or says, "Oh, I've never written an operating system." "Oh, no, I'll write an operating system." And it's subject to the constraint that I can only work part-time, got to write a book and do all these other things. And he redesigned absolutely everything. He said, "Well, if I'm going to do it myself with my buddy, we've got to rethink everything." I think he made one mistake. He redesigned networking. So he didn't do TCP/IP, and Oberon's system can't talk to anything. I think that was a mistake. But apart from that, it's wonderful. So finally, I like to sum all this up. Use contracts where appropriate. Something like UBF, there's only one person using it. Probably your problems aren't difficult enough to need this. Okay? But if you want to isolate clients and servers and do it properly, you should actually have a description, not of the state of the client and the state of the server, but a description of the state of what's in the middle. Use middlemen, make things that fit together, and make software that works. So keep calm, code Erlang. Boom. And that's about it. So, any questions? A man at the back.
Joe, what's your experience with tying together contract descriptions with things like proper or quick check?
I haven't done that, so I don't know.
Could you repeat the question?
Oh, sorry. What's my experience in tying together things like UBF with contract checkers and things like quick check or proper? Answer, don't know because I haven't done it. No experience. But, I mean, I think it'd be a good idea. A fantastic idea. Have you done that?
I have.
And what was the result?
The result was contract worked. The development of the clients was completely independent of the servers, and we put them together, and it actually worked.
First time?
First time.
Yep. The thing about the contract check, it's amazing when you run that. I have done some little projects with contract checkers. And when it says dot, 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 wrong, and you look at it, you go, no, 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 no. Right. I can't see those little spelling mistakes you make and the little things you make. The contract checker sees it and it tells you that's wrong, that's wrong. No questions? Understood everything? Okay, well, thank you very much.